Okay, so welcome back, friends. So today we are going to start from where we left in the last class. So so we are in the last class. I have told you that we will discuss about powder metallurgy. So yeah, today we will start with powder metallurgy processes. So powder metallurgy is basically a near net shape manufacturing process. You can also call it as a net shape manufacturing process, but there are some instances when we need to go for some post machining operations, but they are very infrequent. But often our end goal is to develop the parts in net shape. So it can be defined as the art and science of producing metal powders and utilizing them to make serviceable objects. So there can be several ways to make a definition of powder metallurgy, but the beauty of powder metallurgical processes are that the materials which are otherwise difficult to process using casting or metal forging route, that can be quite easily and effectively can be produced in the form of net shape parts by powder metallurgical routes. Here there are some inherent advantages of the powder metallurgy processes, such as PM parts can be mass produced in net shape or near net shape, eliminating or reducing the need for subsequent machining. So from here you can also understand that there is a lot of wastage that can be avoided in this case. So because in case of like we have discussed earlier, in case of casting or metal forming processes, we often leave the extra metal, we leave machining allowance, so that we can machine down after producing the part. For example, if we are, say, this is a cube that we are going to develop by the casting or forging route, then we have to actually make the die cavity for that cube at least 6 to 10% bigger, so that we can leave the machining allowance. So so this is bigger than this. So if it is A, it is B. So B is greater than A in size. So this is basically so that extra metal that we leave for machining, so that we can achieve the desired surface finish in the part. So that causes a significant amount of wastage of material, like there are some precious metals where this wastage can also may not be economically viable. So there we can go for powder metallurgical routes with minimal or negligible machining requirements. So we can quite effectively reduce the alleviate the chances of machining processes. And also we can powder metallurgy processes are very effective when we deal with micro size parts, where we can get very intricate dimensional attributes. So their powder metallurgy processes are very much effective, which otherwise can be developed by micro machining technique, but that significantly poses challenges in terms of economical viability and also in terms of the machine tool, special purpose machine tools requirement, and also another challenge is the experience of the operator that is needed in case of this precision micro machining operations. So all those difficulties can be dealt with effectively when we will work with powder metallurgy processes. So that some examples are tungsten filaments for lamp bulbs, which are generally made by powder metallurgy route. And so as I told you, it wastes very little material. So 97% of starting powders are converted to product, and it can be made with a specified level of porosity. So another beautiful thing is, so in powder metallurgy processes, as we can get a dense object. So if our objective is to get a dense object, so we can achieve even as high as 99.9% of theoretical density in case of when our goal is to get a dense object. However, we can also go for developing porous parts, where our goal is to achieve significant amount of porosity, like oil impregnated bearings, like wicks in case of spacecraft, loop fit pipe. So these are the applications. So it shows the versatility of the powder metallurgy processes. So we can also develop dense parts, we can also develop porous parts, case to case basis based on the requirement. So, so the raw materials are powder which can be pure elements, pre-alloyed powders. So, the methods for making powders are atomization. So, produces powders of both ferrous and non-ferrous like stainless steel, superalloys, titanium, etc. And reduction of compounds. So, this is another route of powder production. So, production of iron, copper, tungsten and molybdenum can be done in this way, and then electrolysis is also another effective route of powder manufacturing. So, please be careful, we are talking about preparation of the powder. Because for developing the shape, we first need to get the powder with accurate dimensional attributes. So, here one thing you need to understand that there can be several powder particles. So, there can be spherical shaped powder particles, there can be irregular shaped powder particles, there can be there is a great difference between this kind of irregular shaped or regular shaped powder particles in terms of the resultant mechanical properties that we can achieve in the sintered part, which are processed by powder metallurgical route. For example, if you are dealing with these spherical powder particles, then we can basically get much higher grain density. So, they can pack effectively. So, then they can basically form cold welding at the places which are where they are connecting to each other, when basically we are doing the green processing, when we are pressing the powder. So, that cold welding are the regions which then forms mechanical bonding later on, and which in the form of neck formation, and then in the form of fully fledged grains post solidification with minimal post sintering with minimal presence of porosity. Whereas, in case of irregular shaped particles, then there is difficult regions of contact, often not well established. So, that is why post sintering they result in coarser grains, and also there are ample amount of porosity in between, and that causes inferior mechanical properties in the sintered part. So, that is the reason that we need to be very careful about the initial attributes, initial morphology of the powder particles. So not only the process, it is also the raw material which plays a major role in powder processing to achieve the desired mechanical and physical properties. So, the powders along with additives are mixed using mixers, that is the first step in powder metallurgy, and here lubricants are added prior to mixing to facilitate easy ejection of compact from the die cavity that we are being used for powder metallurgy, and to minimize the wear of tools, waxes, etc. and powder characterization. So, like I told you that initial raw material attributes is of high importance in case of powder metallurgy. So, we can classify the initial attributes of the powder particles in terms of size, flow behavior, density and compressibility measures of the powder particles. So, so these are as I already told you, why powder metallurgy. So, powder metallurgy can deal with different kind of materials like metals, ceramics, polymers, etc. and it is capable of doing near net shape processing. It can provide better microstructural control, and also it is effective to develop both dense as well as porous parts. It can develop thermates, oxide dispersion strengthened alloys, and also it can avoid microstructural damage. So, materials difficult to process can be quite easily effectively processed by PM route. For example, reactive and refractory metals, amorphous and glassy metals, and the advantages are achieves a wide variety of alloy systems, facilitates manufacture of complex or unique shapes which would otherwise be impractical or impossible with other metalworking processes. As I was telling you that it can quite effectively get micron sized feature with complex dimensions. For example, if you talk about this tooth gear, so you can quite effectively manufacture it by powder metallurgical route. which is otherwise needed to be machined by gear hobbing or say by milling route, which can become highly expensive. So, we are talking about a micro gear where which can be quite effectively easily manufactured by PM route with much economical manner. So, here so the benefits are economic, benefits are also in terms of properties, because often because we are here we are talking about additive route of manufacturing. We are not so that is why minimal wastage. So, and also better control of the microstructural morphology, and thereby we can control the properties. So, this is an example that you can take for understanding why we will go for PM. So, but it is not advantage alone, every process has some disadvantages also. So, because there is a size effect in PM. So, as it is very much beneficial in case of small size micro size components, it is not so in case of large parts, because in case of large parts you need to have large furnaces to sinter it, which often becomes uneconomical and not feasible also. So, in that case then your conventional sand or permanent mold based casting processes becomes more useful. So, so in manufacturing there is no specific thumb rule. So, it is basically you need to look at the problem in hand, you need to look at that what part you are going to manufacture and what are the end goal, what are the properties that you are looking for in the part that you are going to manufacture, and based on that you should make the material choice, you should make the choice of the manufacturing route. So, in that way because it is a engineering is about optimizing several variants and get the optimum best practice and solution for the problem in hand. So, you have so this is true for manufacturing as well. And so the other advantages of powder metallurgy are maintains close dimensional tolerances. Of course, it provides good surface finish, that is why it is often used for bearing applications, and it provides controlled porosity when our objective is to get a porous object. Like I told you, in case of self lubrication, in case of oil impregnated bearings, and also like wicking structure in spacecraft glue fit pipe, and suited to moderate to high volume component productions requirements. So, these are the advantages of powder metallurgy processes, and the limitations. So, the inferior strength attributes. So, why inferior strength? It is basically because I told you that we cannot achieve a powder metallurgy process part with 100% density. Why? Because although because there are several particles which are being sintered because of the diffusion, they are getting joined at the onset of temperature. However, in the grain boundary triple points there are some pores which are present beyond sintering and beyond completion of the beyond for development of the part. So, these are the pores which are present at the often in the grain boundary triple points. They are basically the weak spots, the weak links which are responsible for inferior fracture toughness. So, of the for ductile material it can be classified as J1C, for brittle material it can be classified as K1C. So, these values are lesser compared to the same material which is manufactured by your casting or forging route. So, so that is a problem, and then there is a high tooling cost involved. Of course, if you are going to manufacture a complex contoured object out of powder metallurgy route, like you, as I told you that you can effectively manufacture it by in net shape, but that often deal with a specially contoured mold. So, that mold cavity machining is also becomes the tooling cost much higher. So, this is there are two halves of the often, if I consider that the preferred powder metallurgy route is injection molding. So, then there is a the male and a female hub of the die cavity. So, there the cavity need to be machined, and that cavity machining can often result in much higher cost, which is otherwise you can get it in case of I mean casting or forming routes, because you can leave extra material for machining. So, you can directly machine down the component post development, and you can arrive at the resultant dimensional attributes in the developed parts. Whereas, because powder metallurgy is a net shape process, we have to machine the die cavity in a effective way, with the dimensional control, with the which should be exact replica of the dimension of the end part that you are going to achieve in the sintered part. So, that is why you have to machine it, and often that machining becomes because generally we make the dies with hardened die steel. So, their machining becomes a challenge and also becomes expensive, whereas in case of cast or formed parts where we are leaving room for machining. So, there we can which are often easy to machine materials like light metals and others, there you can machine them at a much lesser cost, at a much lesser machining time. So, these are the trade offs that you need to consider before making a decision about the manufacturing route that you are going to choose. So, then there is shape and size limitations. So, as I told you that PM is useful for only small size parts, but it is not useful for large components. There casting and forming techniques are proving to be much beneficial, and then there is dimensional changes during sintering. So, as I told you in the previous slide with the example of that cube. So, like in case of machining, the say percentage extra material that we have to provide varying across different material is 6 to 7% more than the actual dimensions needed in the finished part. Whereas, in case of powder metallurgy, we have to make the dies larger by 15 to 20% based on the shrinkage tendency of the particular material that we are handling by to develop the parts out of powder metallurgy route. So, so the dimensional changes can be significant. So, and dimensional change during sintering often comes up with the distortion and associated defects. So, for example, a classic example of, say, if you are going to make a sintering of a cylindrical object, which is a green compact, and then you are sintering. So, then it can face sagging, it can become dumbbell shaped one. So, it is a severe distortion because of the shrinkage and inward diffusion of the matter which is present at the surface of it. So, these are often the time dimensional tolerance control demands extra precautions. So, that is why also increases the cost of the process. So and also because of this non-uniform densification within the part, throughout the part, causes density variation within the part. So, that means we end up getting a density gradient. What do you mean by density gradient? For example, this is again I am taking the cylindrical part example. So, we are using a mechanical press, you are pressing it, and it is kept at the bottom is fixed. So, then only this is a one punch system that you are getting. So, immediately beneath the punch, the material which is present up to a certain distance, it will be the density after compaction will be higher than the rest of the part. So, if I classify this region as say density region 1 and this region as region 2. So, density region 1 will be higher than density region 2, and this density difference at the green compact state will also impact post sintering. So, post sintering also we will get there are more densification in the top part and there are less densification in the bottom part. So, again, so this density gradient will persist, and that is also detrimental in terms of the mechanical properties and the physical properties of the part post sintering. So, this is the case of density variations, and then because of powder, handling with powder can sometimes cause health and safety hazards, and porosity and low ductility that I explained to you earlier, and also it causes low fracture toughness, and the strength and stiffness may be inferior to wrought alloys of similar composition. That is because of the reason of the porosity, presence of porosity in the powder metallurgy process parts, which are often impossible to eradicate completely. So, so these are the pros and cons of the powder metallurgy process, and to alleviate some of the difficulties associated with the powder metallurgy process, like the high tooling cost and also the shape size limitations and also the dimensional changes, here comes the most recent and innovative manufacturing technique, that is the additive manufacturing. So, before going to that, I will just discuss about some of the applications, although I already told you about several application of powder metallurgy, but so you can see this is listed over here. So, it is applicable to automotive, medical, aerospace and all sort of industries, and it is useful for complex contoured micro parts with micro dimensions. So, there it becomes economically useful and also viable to be utilized. So, these are all the applications. So, for encompassing from daily life to several industries we know about. So now we will move to additive manufacturing process, so which is the most advanced manufacturing tool, manufacturing route, and that is what now it is a buzzword worldwide. Why it is so? Because of some inherent benefits additive manufacturing brings into the plate. So, what are these inherent benefits? The inherent benefits are like the demerits I discussed in case of powder metallurgy processes, like the difficulty with developing a complex contour die. So, that can be alleviated because additive is a free form manufacturing. So, here we need not to develop any machine a metallic die to develop the part, rather it gets directly deposited in layer by layer fashion based on the CAD model, that is that is basically getting replicated by the by the building of the part. So, we can based on the energy source, the additive manufacturing can be classified as arc based additive manufacturing, which is called as WAM, and also laser based additive manufacturing, which can further be classified as direct energy deposition and also laser powder bed fusion. So, how they are different? So, in case of you can understand from this image, this is an example of this laser powder bed fusion. So, you can see over here. So, basically the recoater, it distributes the powder layer at the top of the last build, and then the laser cures the preferential region, and also thereby in layer by layer fashion, first layer, second layer, third layer, likewise we basically build the part. Whereas, in case of DED, direct metal, DED or DMD, whatever you may call, in that DED process, basically the laser head and also the nozzle where from the powder gets deposited on the workpiece, in situ the powder gets deposited and laser cures it. So, so it is basically the powder gets deposited with the coaxial nozzle and laser cures it. So, it is a simultaneous process, and yes, one can argue that DED is a material wastage is much lesser compared to laser powder bed fusion, but however, in case of DED the cooling rate is much lesser than in case of LPBF, and we often end up getting coarse microstructure in case of directed energy deposition rather than we achieve in case of laser powder bed fusion. So, so it depends again, like I told you earlier. So, manufacturing is all about making a choice based on the problem in hand. So, it depends that whether you are going to do the additive for a repair work or a cladding work, or you are going to build a micro part with complex dimensions, where conventional manufacturing can become very costly in terms of die manufacturing, in terms of machining techniques, etc. So, in case of developing a complex contoured micro part, I would say that LPBF is a much better technique than DED, whereas in case of cladding or in case of a repair, then you can very well go for DED with a much cost efficiency and economical aspects in mind. So, additive manufacturing, so like I told you, the lasers used in laser based additive manufacturing can be classified as fiber laser or CO2 laser, and diode laser, and materials used in laser based additive manufacturing are metals, polymers, ceramics. So, until now I mean laser are considered as the most important energy source for additive manufacturing. However, the now I mean arc based energy source like worm wire arc additive manufacturing has also has got a lot of traction, where we can directly melt the metal wires and we can deposit them in layer by layer fashion to get the parts out of it. And then there are other variants like electron beam based powder based electron beam based fusion. So, in spite of laser, when we do the powder bed fusion by electron beam, then we call it as EPBF. So, and then there is selective layer sintering, SLS, electron beam melting, and these are all about the solid and powder based additive manufacturing processes. So, now the one of the recent innovations in the additive manufacturing industry is basically the use of the laser as a energy source and then using the metal wires. So, we call it as wire DD. So, and in situ the so these are the, because it is one of the most happening areas of manufacturing with much more promise. So, that is why the innovations are happening on a daily basis, and because of its promise it offers. So, apart from solid and powder based routes, there are liquid based additive manufacturing routes which can be termed as classified as stereolithography, digital light processing, and material jetting. And also there is another technique which is called binder jetting, which is very close to the injection molding, powder injection molding that we have just discussed before, with only difference that in case of powder metallurgy we are using a metallic die or mold to achieve the shape of the part, whereas in case of binder jetting we directly deposit the powder and the polymer mixture in layer by layer fashion without using any metallic mold. So, this is the major difference between other PM routes and binder jetting. So, these are broadly the different classification of additive manufacturing. So, this slide shows you the differences between the subtractive and the additive manufacturing route, and you can see there is a large reduction in waste generation in terms of material wastage. So, here it is much lesser wastage. So, you can very well understand that it is most viable economically for costly materials, and also it can also reduce the efforts involved in tooling, design and manufacturing. So, it is quite useful for precision parts like aerospace, rocket engines, and also it is useful for costly materials with minimum batch production. However, the moment we go for mass production with a much lesser or cheaper material, then again cost wise it goes behind the conventional manufacturing processes like casting or metal forming. So, again that trade off need to be met based on the problem in hand. So, these are basically the advantages of AM over conventional manufacturing routes, like it can produce complex customized parts with shorter lead times and reduced wastage, and the traditional methods offer higher precision, surface finish and well established material properties. So, the choice between the two depends on factors such as part complexity, volume, cost considerations and performance requirements. So, here we compare the additive and subtractive manufacturing routes in terms of lead time, production time. So, of course, additive has a shorter production time, additive has a reduced material wastage, it can be easily customizable, and it can be cheaper to make prototypes, and it can also causes reduced labor cost, because most of the additive processes can be automated with much effectiveness. So, these are the benefits associated with additive processes. So, this is a classic example you can see at the bottom of the slide with the this turbine blade. So, you can see in case of conventional subtractive manufacturing route, basically we are machining down a billet having square cross section, and then we are achieving this profile of the blade, whereas in case of additive route we are basically depositing layer by layer fashion the material and based on the CAD model, and then you can see the amount of wastage is much lesser. So, often we develop turbine blades with I mean costly raw materials like nickel based super alloys or titanium alloys. So, there I mean cost of the material also plays a important criteria, important factor. So, there often we I mean go for, I mean it is recommended advisable to go for additive route over I mean conventional subtractive routes. So, I mean so these are some of the examples of the I mean application of process modeling, because this course we will largely discuss about process modeling aspects. I mean because process modeling is important I mean in many ways, because process modeling I mean deals with the I mean prediction of the best set of parameters which can be I mean considered to achieve the desired quality characteristic in the developed cast part, welded part, or I mean formed part, and even additive manufactured part. So, I mean and also often these routes, like these manufacturing routes, like for example casting of a melt, it is very difficult to understand the how the microstructure is evolving within the solidifying melt, how the I mean thermophysical attributes are evolving over time over during cooling solidification of the melt. So, I mean it is quite impossible, often impossible other than small scale synchrotron study to I mean monitor them. So, we can get a chance to closely monitor these fundamental processes happening in these manufacturing I mean techniques by developing appropriate process models. So, I mean there are several techniques, like I told you in during the introductory class, that we use finite element, finite volume, finite difference, and even boundary element based techniques to I mean solve the I mean numerical models, to develop numerical models of these manufacturing processes. So, I mean in the next class I will discuss about it. So, for this class we will end here, and so see you in the next class.